Hi, everybody. I'm Bryce Adelstein Lelbach. I work at NVIDIA, where I'm a principal architect, and I work mostly on HPC and quantum computing programming models and compilers. I also serve on the Standard C++ Committee, where I chair the C++ Library Evolution Group, and I chair the American Programming Languages Standards Committee. Today, I'm excited to be here to tell you about QODA, our new hybrid classic programming platform. Many, perhaps most, computational fields will benefit from quantum computing in the future. But we expect that quantum-accelerated applications will not execute exclusively on quantum resources. Instead, all valuable quantum applications will be hybrid. Classical supercomputers will be used for large parts of these applications, and quantum computing will accelerate key algorithms. Therefore, tight quantum classical integration is critical. Tools for integrating hybrid quantum classical programming into today's scientific applications are lacking. If you're an application developer or domain scientist today and you want to incorporate quantum computing into your application, you must learn a completely new set of tools and figure out how to connect them to your existing application. We need a programming model for quantum classical systems that is interoperable with existing classical platforms and the tools that we use to program them today. That's why NVIDIA has created QODA, the hybrid quantum classical programming platform. QODA is built to address the challenges that developers face when integrating quantum algorithms into their applications. Our performant and productive NVQ++ toolchain interoperates with classical platforms and frameworks, making it easy to work with existing code bases and techniques. QODA C++ lets you use the powerful C++ programming language to develop hybrid applications for both today's GPU-accelerated quantum computing simulators and tomorrow's quantum hardware. Just as CUDA C++ made heterogeneous computing mainstream, QODA C++ will make quantum computing mainstream by allowing existing and future applications to easily integrate quantum classical algorithms. QODA C++ is a superset of standard C++. It will be an open specification welcoming participation from the HPC and quantum computing community. It's interoperable with common classical programming models such as C++ stdpar, CUDA, OpenMP, and OpenACC. And of course, it's portable. QODA C++ can run on quantum computing simulators or any quantum hardware platform. Let's dive right in with an example. Here's a simple implementation of quantum phase estimation in QODA, which is an important building block of many quantum algorithms. In QODA, you describe quantum circuits with C++ functions. Quantum functions operate on both classical C++ types and quantum C++ types, such as qubits, qregs, and qspans. Those quantum C++ types are just typical C++ class types. They have a familiar interface to both quantum and C++ programmers, building upon familiar C++ constructs like std_vector and std_span. Quantum gates are free functions that operate on quantum types. One of the most powerful things about QODA is that we can leverage familiar classical C++ constructs in quantum code, like control flow, structs, and even the C++ standard library. We have access to all the programming paradigms available in C++, including functional and generic programming. Quantum functions can be generic. They can take other quantum functions as parameters and return quantum functions. They may call other quantum functions. And thus, quantum functions are composable. Let's look at another example, a simple variational quantum eigensolver. Here, we use QODA's spin-op facility. It's an abstraction to describe polytensor products and sums thereof. It's a great tool for describing Hamiltonians. Here, we're using it to describe a 4x4 matrix. Instead of writing the ansatz as a statically compiled C++ quantum function, we can instead define it dynamically using QODA's builder interface. QODA delivers best-in-class performance for quantum classical algorithms. Here's some results comparing the performance of a single VQE iteration with QODA versus a leading Pythonic framework running on a virtual QPU simulated on a single NVIDIA A100 GPU with cuQuantum. The measured time for QODA here includes both the compilation of the QODA C++ code and the execution time. QODA has novel support for asynchronous and multi-QPU execution. Suppose we have some larger Hamiltonian and we want to distribute its execution across multiple QPUs. First, we'll determine how many QPUs you have and how many terms of the Hamiltonian should be distributed to each QPU. Then we iterate over all of the QPUs, and each QPU will get its own slice of the Hamiltonian to work on. We asynchronously launch an observation of each QPU's subterm. The asynchronous launch returns a sender, a handle to the work, which we store in a std vector. After all the asynchronous work has been enqueued, we can then go do some other work while it executes. Finally, when we need the results, we wait for all the asynchronous operations to complete and then sum their results together in parallel with a standard C++ parallel reduction. We can scale a code like this by simulating it on multiple QQuantum vQPUs. QODA will also support vQPUs that transparently run across multiple GPUs. In the last example, we summed up the results of each async observation using a standard C++ parallel reduction. We can do this because QODA interoperates with all of our classical programming models: C++ standard parallelism, CUDA, OpenACC, and OpenMP. You can use all of these programming models together, even within the same source file, and they're all ABI compatible with each other. Here's a great example of the power of this interoperability. In the quantum imaginary time evolution algorithm, we gradually build up a trial quantum circuit representative of the true ground state of a Hamiltonian by evolving it through imaginary time. It's inherently hybrid and iterative. Each iteration, we have to do a linear system solve that depends on the tomography step on the QPU. With QODA, we can do this by computing the expectation values of a spin-op and then use that as the input to a Q-solver linear system solve. The results of that linear solve will feed into the next iteration of the algorithm. There are 4 types of memory in QODA's memory model: host, device, and control accessible memory, all of which are classical, and quantum memory. Quantum code can use control accessible memory and quantum memory. The accessibility of classical memory will depend on the underlying system. On some platforms, host, device, and control processors will be able to access each other's classical memory. On other platforms, the classical memory systems may be disjoint. QODA exposes rich interfaces for orchestrating memory transfers between these classical memory systems. Now let's talk about NVQ++, our optimizing QODA compiler. NVQ++ is based on the Clang C++ frontend. It utilizes QTex, a new LLVM MLIR dialect that we've created for optimizing quantum code. It lowers to QIR, an LLVM IR dialect for quantum code generation, as well as other quantum intermediate representations. NVQ++ parses QODA source code, building an abstract syntax tree. That AST is lowered to a classical IR and compiled using a classical toolchain, producing a classical object file. During this process, the classical compiler replaces the quantum functions with thunks, which will be filled in later by the quantum compiler. At the same time, we extract the quantum functions from the AST. Those quantum functions are then lowered to QTex. We iteratively perform both classical optimizations and quantum-specific optimizations on that QTex representation. Then we code gen from QTex, targeting QIR or a partner backend, producing a quantum object file. Finally, a classical linker combines the quantum object file and the classical object file. And that will connect the quantum thunks in the classical code to the quantum code, producing a working QODA program. QODA supports 3 different compilation modes. In the portable compilation mode, QODA is compiled by any existing classical C++ compiler without using NVQ++. This will produce a working QODA program, but it must target a simulated QPU backend, and the program won't benefit from NVQ++'s specialized quantum optimizations. In the standalone compilation mode, NVQ++ is used as both the classical and quantum compiler. This mode will produce an optimized QODA program which can run on any QODA backend, simulated or physical. However, the program won't have the benefit of programming model interoperability, so you won't be able to use C++ stdpar, QODA, etc. Finally, there's the partner compilation mode. In this mode, NVQ++ is used as the quantum compiler, and a supported C++ compiler is used as the classical compiler. This will produce an optimized QODA program that can run on any QODA target and supports interoperability with all of our classical programming models. The only downside to this approach is some productivity limitations, such as slower compilation times. Now let's talk a little bit more about QTex, which is our new LLVM MLIR dialect. It's a high-level compiler intermediate representation that can describe both classical and quantum code. It's a single static assignment IR, so quantum operations will consume qubits and produce new qubit values. It leverages existing classical optimization techniques, but it also adds quantum-specific optimizations. While we primarily use QTex for C++, it's front-end agnostic. We expose an API to QTex so that it can connect to other front-ends. QTex lowers to the QIR LLVM IR dialect, as well as partner intermediate representations. Now, let me show you an example QTex optimization, identity pair removal. The QODA source is on the left, and the unoptimized QTex MLIR that it produces is on the right. As you can see in the source, we have 2 CX operations that will be performed on the same 2 qubits, and thus will cancel out. So first, we perform a classical optimization, inlining, and that will inline the quantum function f. And so now the compiler can see that we have those 2 CX operations on the same qubits. Next, we'll do a quantum-specific optimization pass, which eliminates those paired CX operations. Now we have nothing that actually operates on the qubits. We just allocate them, and then we deallocate them. So when we run another classical optimization later, dead code elimination, it will remove these qubits entirely, as they aren't used and we don't need them. And this will leave us with an empty function. This example shows the power of combining classical compiler optimizations, such as inlining and dead code elimination, with specialized optimizations that understand the semantics of quantum operations. As we all know, all valuable quantum applications will be hybrid. And that's why we need QODA, the hybrid quantum classical programming platform. With QODA, you can use the powerful C++ programming language to write hybrid applications that interoperate with today's most popular classical programming models like C++, stdpar, and QODA. That code can be compiled with NVQ++, targeting both GPU-accelerated quantum computing simulators and quantum hardware. NVQ++ uses the QTex MLIR optimization pipeline, which combines classical compiler techniques with novel quantum-specific optimizations. We'll be announcing a beta for QODA later this year. If you're interested in learning more or collaborating with us, please subscribe to the mailing list on our website. We're excited to hear from you because QODA is an open, hardware-agnostic platform, and we want to work with the whole quantum community to build it. Thank you all for your time.